So how many people in the audience are kernel developers? Oh, few? Okay, awesome. So that'll make the slides at the beginning go good for those people who are the non-kernel developers. So I'll just introduce myself. My name is Robin Getz. I've been involved in open source and the Linux kernel for longer than I would like to admit. I'm not here on behalf of my employer. I used to work at Analog Devices on the open source stuff, and this is kind of a continuation of some of the projects I started there. I've been involved in Linux basically since you had to install it off 29 floppy disks. And that doesn't mean that anybody who's old is not necessarily experienced, but we'll just kind of go from there. So for anybody who wants, I'll definitely send the slides to you if they're not available online, but they should be, I think, tomorrow or after the event is over. So just for those non-kernel people in the audience, the purpose of the kernel is to manage, is basically 4 different kind of things. One of them is to do the memory management. One of them is to manage processes, make sure different tasks and different applications are scheduled the right time with the right priority, manage hardware, that's the device driver piece, and do system calls and security. Those are the kind of the 4 major things the kernel does. And it's the kernel's job to really manage the hardware. And what I mean by that is like turn it on, turn it off, allocate to users, pass data back and forth, those kinds of things. And there has always been, for probably the last 10 years, kind of this concept of user space drivers. And user space drivers are great, but they're also terrible. And what I mean by that is that they are great from a developer perspective. You don't have to be a kernel expert to write a user space driver. So you can save yourself some headache. The disadvantage of you don't get to use the kernel infrastructure that is there to make your job as an embedded engineer actually easier and more performant. So when you think about these things like accessing resources, complexity, performance, doing things in a in-kernel driver is definitely the way to go from that perspective, but you must be this tall to ride this ride. There is a complexity that goes along with that. And you know, when I look at things, when people talk about like user space drivers, which is a lot in the embedded industry because it's actually more about developer skill set than actually what is the best technical thing to do. So, you know, when people talk about user space drivers, some of the times is developer skill set, some of the times is like, oh, we need to protect this intellectual property of this device driver. And typically the conversation I have with those kinds of folks is, are you really trying to protect intellectual property of transferring data from a sensor to something in user space? That's not intellectual property, that's sweat equity. And just because it took you a long time doesn't mean it has value. And so you need to split those kind of 2 things apart as you're having these discussions with your managers or even sometimes yourself about, you know, what is the best thing to do to get the performance out of the system. Now, that doesn't mean the Linux kernel isn't complex. There are a lot of different subsystems in the Linux kernel, from device drivers being one of them, to the memory managers, to buses, to SPI, to I2C, to USB. And IIO, or the Industrial Input-Output Framework, is just another one of those frameworks inside the Linux kernel. Just like audio is, just like video is, just like PCI or you know, power, frequency, file systems. All of those kinds of things have their own separate subsystem, their own separate development teams, all of these kinds of pieces. And that's what we'll go through. So if we kind of think of audio, which everybody kind of is familiar with, the audio stack, there's the hardware, there's some DMA, there's the ASOC framework, there's the ALSA framework, there's the libALSA up at the highest levels. And that's kind of where it comes from. And IIO is a very similar kind of stack where you have hardware, you have different types of hardware, you have different buses, you have I2C, you have SPI, you have different variety of things, depends how your sensor's connected, even USB. But then that kind of, as they go up the layers, it looks very close to the audio stack as well, even with like a lib IIO at the top layer. So all of these things are like, if you kind of understand one subsystem, the subsystems in Linux are very close architecturally, the way that they actually can be used, both from in-kernel developer standpoint, the person writing the device driver, as well as from an application standpoint, the person using that device driver. And those can be different people with different skill sets. So the IIO framework in Linux, it was really like for sensors. So before this was developed around 2009, there was a subsystem in the Linux kernel called miscellaneous. And that's where everybody jammed everything. And it was a good idea at the beginning and then a terrible idea at the end. So devices got put in miscellaneous, they got put in hardware mon, they got put in human interface, and there was kind of a big mishmash of different places, and it became the person who wrote the device driver did the application, and it was very like combined. IIO tries to separate those things and make them a standard format so you can kind of access things in a standard environment, specifically from a sensor standpoint. So whether that's just a raw ADC or DAC or an analog to digital converter or a digital to analog or an analog to digital or a digital to analog, or accelerometer or gyro or IMU or pressure sensor or DDS or direct digital synthesis or phase lock loops or color or light or proximity sensors, all of those kinds of sensors now belong in this IIO framework. And that was developed in 2009 by Jonathan Cameron, moved out of staging in about 3 years later. And then there was just recently a high-speed DMA interface added just about a year ago. And in terms of who's developing things, just on the driver's side. So this is just the in-kernel pieces. So we can actually see the number of files in staging kind of like go up for the first year, like you would expect, and then as things solidified and became common, everything just went into the standard drivers IIO directory. And you can see the number of files is almost like 700 files now. And that equates to about 250,000 lines of source code, supporting, like one file will support 5 to 10 different devices. And we'll see like that is a large number of people doing this. So when you look at the number of contributors per release, it goes anywhere between 300 people and about 50 people working on this on a daily kind of basis, chugging along, adding device drivers, adding infrastructure, coming up with different use cases, closing the gaps on those use cases, figuring things out as we go along, just like any kernel subsystem does. And then when you look at like the number of total unique contributors, it's also continuing to grow. Now with over 1,000 people have contributed to the IIO subsystem. So this is actually one of the faster growing subsystems in the Linux kernel because of the embedded nature of things. And when we look at who's doing that development, it's not surprising, it's a lot of the semiconductor vendors. It's people like, and this is, I just organized alphabetically, but ADI and ARM and Freescale and TI and the standard kind of vendors that you would think would be doing devices because when I was working at a semiconductor vendor, we would go talk to customers and their request would be, have a mainline driver or I don't use your part. And more people need to tell their vendors that. That is the only, like, you should not have to write as an OEM device drivers for parts that everybody else is going to take advantage of. That's the job of the semiconductor vendor. And then there are also the third parties, the consultants who do that for remuneration. And then there's like a lot of end users as well. And it's everybody from National Instruments to Chromium to a variety of different things. Even on your laptop, the accelerometer in your laptop and in your Chromebook uses IIO to do fall detection, to do all kinds of things so they can park the hard drive before the system hits the floor. And so it's a variety of different systems. Or the ecosystem of developers is really driven by the semiconductor vendors, but there's also lots of other people doing it as well. And there's actually quite a few Google Summer of Code people that do device drivers as well. If you are a semiconductor vendor wanting to mentor people, it's definitely a good thing to do. And then what kind of devices are actually in the IIO framework? You can kind of see along the left-hand side all the different types of sensors that all have a common framework now. So you can actually move from one vendor to the next vendor. Your application can stay the same. The kernel API stays the same, but then the device driver just changes. And that's what you want from an embedded system. You want to be able to have that freedom, to be able to get either the best part for your application without having to change your software all around. And then always the vendors have their repositories where they have work in progress. So both ST, AMD, ADI, Microchip, NXP, they also have their Linux kernels up there with device drivers that are done and being process of upstreamed or done or in process of being rewritten so they can be upstreamed, just depending upon who does those kinds of things. Now, the high-speed interface that was upstreamed, prior to about a year ago, every different subsystem in the kernel who wasn't the DMA subsystem wanted a custom DMA framework for their interfaces. And that was everything from GPU or like video for Linux folks. They actually wanted a separate kind of like tweaks to the DMA framework so they could get things to the displays, the GPU wanted a separate thing to have to talk to PCIe cards for doing multimedia encoders, and the DMA team naturally got super frustrated with it and said, hey, we need to come up with a common way to do all these things that works common across subsystems, and that's what the DMA buff turned into. And so then IIO started taking advantage of that to get very high-speed read-write access to DMA subsystems. And so now, like IIO will support anything from multi-gigabit ADCs and DACs to IMUs that are like updates per second, which is pretty great. So, but it's also application level control, not just part by part by part level control. So in the IIO subsystem in the kernel, in your device tree, you can actually specify these devices are chained together. And in this situation, there's like a ADC DAC with PLLs and filters and a variety of other things, so that if I change a setting in a PLL that changes the frequency, which causes a change to happen in a filter, that can automatically be done in the kernel without having to do everything in user space. So it makes it much, much easier and much faster because everything is just like a single system call, and then everything all happens automatically from there. So by having different vendors, because your embedded systems are not typically made from a single vendor, all working in the same subsystem, you can chain these things together and they all work from a common framework, which makes it much more powerful. Now, some of the concepts that we have in IIO, there's a context, which is a group of devices. So it's typically a single system is a context, and then I can have multiple devices. Each device can have attributes. So a device can have an attribute. A device can also have a debug attribute. And those debug attributes show up in the debug FS. And those are typically things that kernel developers or the device driver developers want to use to poke at something that's not always exposed, just like the back door to trying to get at things when you're not sure what's actually happening. And then you can have buffers and channels. So you can kind of expect that a device may have multiple channels or multiple buffers depending upon what the type of device it is. And just like multifunction chips, the multifunction framework in the Linux kernel, some vendors have decided to split up their sensors or their chips into multiple different devices. So one chip may represent 3 devices. Because of integration, Moore's law, that kind of makes sense because it is really 3 different devices from a topology standpoint. It just happens to be in a single package or a multi-chip package or on a single die. It really doesn't matter from that standpoint. But what we get to do now is we can split them up logically from a software perspective and not have to worry about the physical implementation of the parts, which is kind of, it splits up that physical to logical mapping. So with IIO, there are 2 main use cases. So typically, the deployed use case or the local use case where things are running on your Raspberry Pi or your embedded target. And this is, standard Linux kinds of things that'll run, no problem. So I have a device that we made at ADI. It's a software-defined radio. So inside of this, there's a Zinc 7000 SoC from Xilinx that has a dual ARM core device. So we actually run Linux in the box. And it kind of runs in this kind of configuration. So IIO actually runs on here and then serves up pieces to other devices. And that's kind of like the next use case, the development use case, where we run a daemon that serves up the data over USB or over Ethernet or wherever you want to be to your development machine, whether that be Windows, Linux, Mac. So you don't have to do all your development on your embedded target. You can actually do your algorithm development on your host, just like normal, and still capture the actual data from your device. Because that I think is like the biggest kind of power of IIO is the libIIO aspects, which are built in to not only access the devices themselves on the local piece, but also access things remotely. Because it does make development much easier when you can capture the data from your sensors, from your control systems in a pseudo real-time manner into your PC, and then work on it from Python or from MATLAB, or give it to your algorithm engineer who's traditionally not a embedded engineer, and kind of go from there. So moving from remote, or from local to remote, back and forth. So on local, when I create a context, I just say IIO create context from URI and say local. And when I want to do it remotely, I just say create context from URI and give it an IP number or a USB address or a serial port address. And that IP can be over wired or wireless or 10.1L, or the serial port can be over Bluetooth. It can be a lot of the physical transport mechanism doesn't matter that much. And also, you can kind of see the different kind of back ends, as we call them, that it supports, these transport mechanisms. So we support MDNS to do discovery. We support a variety of different things to try and make development easier for people. Because one of the minor reasons we decided to do like little boxes like this was so we could ship things in volume and get tens to hundreds of thousands of people, that's kind of what we shipped of this thing, to try it out on their desktop and report bugs to us, to make sure that it was all solid so that when aerospace defense companies used it in rockets, we knew it was going to work. And they do. So again, moving from remote to local is just a one-line change. So whether you're device or channel attribute, it is a true RPC. So you don't, all the calls about the devices and channels and the data is all the same. Where it runs is different. Here we're running on the device itself in our embedded target, and here we're running on our Windows machine, or our Mac, or our Linux development host. But it's that RPC type of mechanism that makes that possible. So you just need to recompile for ARM, depending if you have an ARM laptop, you don't even need to do that. So most of the time when we write applications, or when I write applications, the string that you create the context from is just given to you on the command line. So you run the command, you say where it is, and then it just goes and captures it from there. And so you can run it on your host, you can run it on your target, it really doesn't matter, and it all runs the same. Which is, I think, super powerful from an embedded development piece, where your hosts are much more powerful and you have a much richer debug experience than you will on your, even your Raspberry Pi, which is pretty good compared to what people suffered through from before. So the transport layers are what we call backends. We support like local and network, USB. There's some work going on for PCIe and serial port. And that's really, that backend keeps track, or eliminates the need for you to worry about that low-level communication piece. And those hosts on the remote host side can be MATLAB, can be Python, it can be Julia. It should be meeting your algorithm engineer where they already are. You shouldn't have to learn a new environment because you want to try and program or capture data. Somebody interested in doing Kalman filters is not interested in doing it at low level on your embedded target. They want to do it in MATLAB or in a higher level of abstraction like Python or MATLAB. And this allows them to do those kinds of things. So that's where IIOD comes into play. This is part of the user space library. So we have a daemon that basically serves things up over a variety of different transports, like I talked about before, whether that's USB or Ethernet or serial, to abstract that communications piece. There are some improvements that we learned a lot doing like the first version of IIO, or LibIIO. One of the things that people told me a long time ago when I first started out my career is you never use version 1 of anything, which is probably pretty good advice. And that's why we've been shipping LibIIO for about 10 years, like version 0.26, those kinds of things. When LibIIO 0.x was introduced, it had a very TCP-like streaming mechanism. You asked for a packet, we sent you some data, you acknowledged you got it, we sent you some more data, and that kind of request acknowledgement consumed actually a lot of USB traffic. So on USB 2, which is half duplex, we would lose about 40 to 50% of the performance just from like acknowledging packets back and forth and having to flip the bus around. So in libUSB 1.0, we kind of changed that paradigm, made it a little different to do, but now it's really streaming that data buffering model so that we can actually consume 100% of the maximum bandwidth of these transport mechanisms. Because you say, just send me data, and it starts sending data until you tell it to stop. There is a compatibility layer for those people who do have, LibIO, like 0.x kind of applications already written. We've moved to pointer return functions, so like pointer returned error encoding, which makes it a little bit more consistent for people. And we really tried to drive this kind of like, cleaner, safer, greater reliability, improved C++ experience, and then like easier migration. And kind of like that's helped drive some of the platforms and language bindings. You can find LibIO in most of your favorite distributions already because of things like this. This is actually pretty popular. And a few other devices like that from other folks as well. It does compile for Android, so you can actually have an Android application that uses LibIO that communicates over USB or Ethernet to your remote device. Mac, Windows, and then from a language perspective, it's C, C++, Python, including like pip and PyPy, C#, and then there's external bindings for Rust, Julia, MATLAB, and Node.js that other third party have done based on their desire to do their algorithm development in whatever languages they were comfortable with. So at Analog Devices, for example, they had a lot of C# developers, and most of their GUIs for their evaluation boards were all based on C#. So we made the C# interface so they could actually run their evaluation software and connect it to Linux IIO kind of device drivers so that they could actually, your evaluation platform was the same device driver, 100% source code compatible with what you were going to ship in your end product. So test what you ship, ship what you test. It's that kind of like philosophy. And that's what enabled these things. So the Python interfaces, they are kind of Pythonic. So I'm not a great Python developer, but you know, in a few lines of source code, you know, everything, you can get objects, you can, instead of having attributes, there's the properties, same kind of thing, where, you know, you're doing it in the native Python kind of way to interface to these devices. And the same is true on the MATLAB side. So in a few lines of code, you can be able to get FFTs and go from there. And it's just, you know, here's an object, set the attributes, and then go from there. Set the properties in the MATLAB objects and go from there. And then just kind of as an example, this is a IMU on an interface board connected up to Raspberry Pi, which is running, ADI's Kuiper distribution. And what they're doing is just from a MATLAB perspective. So here we instantiate an object, which is IMU is equal to ADI, ADS 16480, which is the device. That'll instantiate the MATLAB object, go from there. So then we just configure the object parameters, which would be the URI, the number of channels, because there's a variety of channels inside the IMU, and we're only going to capture the accelerometers and gyros, and then set it up for like numbers of samples and those kinds of things. Then we, oh sorry, I should have sped up the video a little bit. Stream the sensor data using like the read. So we just take the object and do the read command, just do the read property on it. And then we have a system set up, which is basically a motor. And then there's a battery, the Raspberry Pi, the interface board, and the IMU itself. And we can just see here, we're just, you know, typing away, getting the property, set the URI to be the IP address. It tells us, you know, what the sample rate is, what the read mode is, the samples per read are. We only capture the first 6 channels, which are the accelerometer and gyros. And then we just do a read and we get all the accelerometer and gyro channels. And you can see the accelerometer provides data in G, so everything comes back in nice SI units. There's not like bits you have to try and remember and like translate over. So the interface from an IIO perspective is SI. And then we can take this and we can actually like capture data, because on the device itself is capable, I think, of 100 readings per second. And we can just run a little script on this device and just do some plots. Look at the IMU data, look at the acceleration, look at the angular velocity as things are spinning on the little tripod with the motor stuck to it. And then then we can actually take this and do a little more sophisticated things, like take this little box, which is a 3D object in MATLAB, and actually cause that to spin at the same rotation as the IMU does. So, here we turn the motor on, and we can see that spinning, and we can see the system spinning as well. And you can kind of see the battery in the Raspberry Pi a little bit better now, too. But you can kind of get the idea. It actually does work. It's, 15, 20 lines of code, because a lot of these things have been extracted. You don't need to know the interface. You can switch out the IMU. You can do all these kinds of things, and your MATLAB code hardly changes at all. So from an algorithm developer standpoint, it becomes much more powerful. So this will also scale. So this is a quad 16-bit, 12 gigasamples per second RF DAC, and quad 12-bit, 4 gigasamples RF ADC in a single package. And we do the same kind of things. And we interface to a variety of different software packages that support IIO, from SDR Angel to GNU Radio, to MATLAB, to a variety of different packages that are up there that I can hardly read anymore because I'm just at a weird angle. But, from Rust to Chrome, all these kinds of things you can actually develop and get going yourself. And you don't have to worry about which device it is, or who's actually doing that device driver piece, because it all looks the same from a user space standpoint. You can switch from this to RF SOC from Xilinx or AMD, and your application doesn't actually change. And the benefit of doing these kinds of things, if you kind of think of this like OSI layered kind of model, is if we have our hardware, and in this case we have an FPGA, and our embedded kernel, and our embedded user space, and our host, we have nice defined layers in between. And so you want to control things. The biggest challenge that most people have with embedded stacks like this, which is kind of like similar to lots of people's stacks, is when a problem goes wrong at the final stage, trying to triage where the problem is. Is the problem a HDL problem? Is it a software problem? Is it a device driver problem? So unless you can separate these pieces logically and test them unit by unit, it's very difficult to find out where these problems exist. And that's one of the things that IIO actually does provide. Because it has this natural kernel, user space, application, signal processing environment, you can split them up and actually figure out where these kinds of problems exist. And focus on the pieces that you are interested in. So, for example, if you are a device driver person, you can write the device driver and then just test it with everybody else's user space. You don't have to worry about trying to write your own data capture application and making something like FFTs and applying window functions and all the things you didn't like to do, which is why you write device drivers. Or vice versa. But, if you're the algorithm developer, you can focus on those pieces and not have to worry about the bits and registers trying to figure out reading data sheets. Because hardware data sheets are written by hardware engineers for hardware engineers. They are not written for software people. And it's this, how do I separate things? How do I ensure that things are working? And this is the big advantage I always think of doing things in an in-kernel device driver way rather than a bespoke thing in user space, is it forces you to comply with this kind of environment, which lets you take advantage of the stack. But it's focusing on the level you care about, and how it fits into the larger system also kind of helps determine whether you can use these things or not use these things. And when they are industry standards and you can use them and reuse them, split them apart, be able to debug them, it becomes a much more powerful environment, and you're not left like, I've talked to like engineers who used to work for me, and they're like, how long is it going to take you to debug this? What's your strategy? And he's like, I don't know, I just have to stare at it long enough. And that's never a great debug strategy. It's like, well, how are you going to break it down? And everybody's been there. That's the problem with the embedded environment. So, one of the things we did is like, you want to be able to isolate and debug these things at different layers, which is why in LibIO we also provide command line tools, just like aplay, arecord on the ALSA side. So these are command line tools, IO info, IO attribute, read dev, write dev, registers, to let you do low-level read and write to SPI or I2C addresses. So that if you are a user of the device driver and you configure the part in a certain way and you're sophisticated enough to read the data sheet and say, okay, this register should be this at this point in time and it's not, then you can go to your device writer and complain. And it's great from a person who's writing the device drivers just to make sure that they're doing what they think they're doing. As well as just capturing buffers, making sure the devices are being configured properly. And we can do that at kind of that IIO level. You don't have to worry about MATLAB. You don't have to worry about Python. These are just command line utilities who do nice command line things. But they still will run locally or they will run remotely as well. And that's great. It became like very evident how good it was when during COVID, when we had like one piece of hardware in the lab that everybody was kind of sharing, but everybody could remote in. You didn't have to remote into it. You could just talk to it from your machine, which was nice. But it's not just for, IIO is not just for Linux anymore. When I was at ADI, there were enough people that said, okay, well, I want to actually take my algorithm that I developed on my Linux environment with Raspberry Pi and actually move that to my microcontroller environment on Arduino, where I don't have a POSIX environment. So what we did was we actually made what we call Tiny IIOD. And it's really meant for NoOS or FreeRTOS or Zephyr kind of environments. So you can do the similar kinds of things, but then not have to throw out your development environment on your PC, so your algorithm developer still has the same kind of Python interface or C or MATLAB, so they can do those pieces on their Arduino system. So this makes, it's supported just over serial and Ethernet and Wi-Fi right now, but it does add some complications into LibIO because depending how you configure LibIO, now it can either turn out to be an MIT version or a LGPL version. So one of the things that we did, which is still kind of in progress, we actually have like a license check CMake option. And when you do that, it'll actually use the CPU processor, go through all the source code as it's configured and as it's built, and look for the SPDF license lines and actually just keep track of them. And if you see ones that say LGPL, then you know that it's LGPL. And if you see ones that say external libraries, then it's up to you to go through those external libraries and make sure you're license compliant. But that way, when you are building it in a microcontroller environment, you can make sure that you're not including something by accident. The other thing that we've done is done an IIO emulator. So for those people who are in the embedded space, those first 10 prototypes you have that are working are gold. And everybody wants them, and the people who need them can't get them. So what we did basically is create a mock of an IIO device. You point a application called XMLGen to a real IIO device. It'll capture that context in an XML file, and then IIO emulation, IIO EMU, will serve on the network up an emulated context for you. So that way you don't have to have the piece of hardware beside you. It doesn't do things like look for out of bounds or cause things like, you can definitely send things to the emulator that will cause your hardware to blow up, and the emulator will be totally fine with that. It's really meant to, but it's meant to help your application and algorithm developer kind of like get going while you're building up your hardware, well, especially in those first stages, so they can get something that's going to be close, but not maybe exactly right. And this has actually helped quite a bit. You can feed files in, so instead of reading ADC data, you actually just get to read the file, but it comes through an IIO context. So your application can be very, very close to what your real application is going to be when you get more hardware available. So the other thing that we've done in IIO 1.0 is use, or working on, is use DevMem. So DevMem is a concept on the Ethernet side to actually have 0 copies in the Ethernet stack. So you can go directly from DMAing ADC data to non-coherent memory, and then that goes right out to Ethernet with no mem copies in the kernel, which is a big, big improvement in terms of overall throughput. And ADI is using this right now for some higher speed devices, even at the 40 gig Ethernet kinds of interfaces for their higher end converters. And again, MATLAB and system blocks, they use like IO under the hood for a lot of these different pieces. So when you communicate to these radios, it's really just SDRRX and then tell it what device it is, like Pluto, which is what this one is, and then Simulink does the similar kinds of things. So I think that LibIO does support like running locally on the target with little or no changes in terms of like the host, sensor interfaces, networking interfaces, ZeroConf, all those kinds of things. There's a lot of different popular IO clients that you should be able to use. You don't have to develop everything yourself. And there are a lot of IO devices, like from the Xilinx development kits to Raspberry Pi to ST to ADI to NXP to even some of the education kits. So I'll just wrap things up, and then kind of open things up for questions. IIO Subsystem is in the Linux kernel. It's been there for at least 12, 13 years. It does give you that remote access, lets you do that host-based algorithm development. It's really meant to speed up your development process. And that's kind of like the main takeaway that that when we were developing this, we wanted to do is what are the major pain points that people have developing their embedded systems? How do we help solve those things? And thanks very much. There's definitely some time for questions. I don't think anybody's kicking us out of the room. But yeah.
Testing. How does IIO relate to the older Comedy subsystem used with data acquisition cards?
So Comedy and IIO are kind of orthogonal. Like Comedy is really for PCIe, and that's not something IIO really supports. IIO is really for the embedded targets as opposed to the plug-in card kinds of things, where Comedy is still being developed.
Yep.
Does that make sense?
Yeah, that makes sense.
Okay. Here.
Sorry to make you run all
Oh yeah, no problem.
What is the preferred solution for handling precision timing? So if you've got like inter-sample timing in the buffer and between different nodes within the tree that might be like disparate devices, even if they're in the same package?
So there's definitely a timing and trigger mechanism built into IO specifically for that. So we've done some tests with like PTP and even across nodes seen the ability to simultaneously capture samples across different devices. But yeah, there's a triggering framework and sample timestamp framework in there for the lower speed devices, not for the high speed devices. That's something they're still working on right now.
Oh, do you know when, like what I'm interested in the high speed end of things.
Oh, okay, okay. So on the high speeds.
I gave a talk about that earlier this morning.
Oh, okay.
So I can talk about it more now? Or
Sure. Yeah.
Yeah, so for those of you who are in my talk, I'm Dave Lechner at Bay Libre, and I recently became one of the three new reviewers for the IIO Subsystem. So the last 2 years, I've been very involved with ADI upstreaming analog stuff in the kernel. And one of the projects I worked on over the last year was what we called SPI offloading. So like you're talking about, we're dealing with ADCs that are running at 1 million samples per second, and you need very precise timing.
So that's what the question is, like, what's your definition of high speed? Gigasamples per second. Yeah. So typically on an FPGA. Yeah, okay.
Okay, yeah, so we did it for SPI, but for FPGA, you would do all the precise timing in the FPGA and dump everything in a DMA buffer, and then the IO system can handle that DMA buffer or what you're talking about. There's other ways to hand off that buffer, zero copy, to other subsystems to send that data somewhere else. And that's also landed upstream within the last year as well.
But so I'll definitely be around if people have questions, and I think David will be as well. But I think we'll have to wrap things up because we are a little bit over. So thank you so much.
Thank you.
Thanks.